Hi students, in this section, let's try to understand what we mean with prime and composite numbers. Before we get into these two types of numbers, as a background knowledge, let's try to revise what we mean with factors or divisors. Let's take an example. If I divide 6 with 3, I'll get the answer as 2, right? And the remainder obtained is 0. You can see that the remainder is 0, right? Now, because the remainder is 0, I can say that 3 divides 6 perfectly. Now, 3 is a factor or a divisor of 6. Therefore, you can see that what we call as a factor or a divisor is a number that divides the given number perfectly. That is, leaving no remainder. Alright, now we know what a factor or a divisor of a number is. With this knowledge, let's try to understand what we mean with prime and composite numbers. Let's start with prime numbers. These are numbers with only 1 and itself as factors. Only 1 and itself. Let's take an example. Say you take the number 5. What are the numbers that can divide 5 in a perfect manner? You will see that the factors are only 5 and 1. What do I mean with that? If you divide 5 with 1, you will get the answer as 5 and your remainder is 0, right? If you divide 5 with 5 itself, you get the answer as 1 and your remainder is 0. But for example, if you divide 5 with 2, you will get your answer as 2 but the remainder is 1. So 2 is not a factor of 5. Therefore, we have seen that 5 has only two factors, that is 1 and itself, and hence 5 is an example of a prime number. Alright, now what is the smallest prime number? Let's just think a little bit more about prime numbers. The smallest prime number is 2. You can see that 2 only has 1 and 2 as its factors. 2 divided by 1 is 2 and remainder is 0. 2 divided by 2 is 1 and the remainder is 0. Please note that 1 is not a prime number, right? Prime has to have two factors, right? 1 and itself. In the case of 1, it's just 1 and 1 is not a prime number. The smallest prime number is 2. Alright, now let me make some space over here. So we are clear what we mean with prime numbers. Let's see what we mean with composite numbers. So composite numbers are nothing but numbers that have more than two factors. Anything that's not prime and is not 1 will be a composite number. Alright, let's take an example. Say let's take the number 6 and let's think of what are the numbers that will divide 6 perfectly. You will see that 6 has 4 factors, 1, 2, 3 and 6, right? If I divide 6 with 6, I'll get a remainder of 0 and the quotient is 1. So let me write that over here. 6 divided by 6, the quotient is 1, the remainder is 0, right? 6 divided by 3, the quotient is 2, the remainder is 0. 6 divided by 2, the quotient is 3, remainder is 0. And 6 divided by 1 gives me 6 and the remainder is 0. So these are the 4 factors of 6, and because 6 has more than 2 factors, 6 is called a composite number. Now that we know what we mean with prime numbers, let's try to understand what prime factorization is. This is an important topic and it's used in many different types of concepts and chapters in maths. Alright, now prime factorization means writing a number as a product of its prime factors. We know what factors are and we know what prime numbers are. So when we write a number as the product of prime factors, we call it prime factorization. Let's take an example. I can write 12 as 4 into 3, right? But over here, you can see that 4 is not a prime number, right? 4 is not a prime number. It has more than 2 factors. The factors of 4 are 1, 2 and 4. You can see that there are 3 factors, right? So writing 12 as 4 into 3 is not prime factorization. So if you're trying to do the prime factorization of 12, you should be writing it as 2 into 2 into 3. Over here, you can note that all these numbers are prime numbers. 2 is a prime number, 2 is a prime number and 3 is a prime number. They only have 1 and itself as their factors. Now let's try prime factorize 980. All right. So basically we have to write 980 as the product of prime numbers. That's what we are trying to do over here, right? Now let's try to take note of a method which we will be using to accomplish this. So I write 980 over here. I draw a line like this. Now let me think what factor I can take out. So taking out and factor means dividing 980 by that prime number. So I can see that 980 is divisible by 2. So let me take out 2 and I am left with 490, right? Now more about these divisibility rules we will be discussing in the section on divisibility rules. That will help you to do prime factorization in a much faster way. But let's go on now. So 490, that's what I have now. I can see that I can still take out 2 from 490. So let me do that and I am left with 245. So 490 divided by 2 is 245. Now 245, I can see that I can take out 5 from 245. 5 divides 245 perfectly. So let me take out 5 over here and I am left with 49. 245 divided by 5 is 49. Now I know that 7 square is 49. So I can take out 7 from 49 and I get 7 over here. And 7 is a prime number. You can either leave it like this or you can write taking out 7 again and you're left with 1. Now 980 will be the product of all these numbers, the numbers that you have taken out. That is 980 is equal to 2 into 2 into 5 into 7 into 7. You can note that in these two cases we have only used prime factors, right? That's an essential criteria when you prime factorize a number. One more interesting observation. Over here you have two 2's and you have two 7's. So you can write this in a different format that's commonly used. You can write it as 2 to the power 2 into 5 into 7 to the power 2. Over here you can note that you have a power 2 because you have two 2's, right? Similarly, you have two 7's. That's why the power over here is 2. In case you had 3 7's over here, instead of 2 over here, you would have written 3. Hi students, in this video, let's get introduced to the concept of a variable. Alright, so what is a variable? A variable is a placeholder for a value we don't know yet. Alright, let me take an example to explain this better. So find a number such that half of the number is 5 more than 1/3 of the number. Alright, now we need to find this number. We don't know the value of this number yet. So let's use a variable to represent this number. So let me take this number as x. Now you can see that a variable is typically an alphabet. We take an alphabet as a variable. Alright, so this number is taken as x. Now it's mentioned that half of the number is 5 more than 1/3 of the number. So half of the number would be x divided by 2, right? Because we have taken the number as x. Alright, now this is equal to 5 more than 1/3 of the number. 1/3 of the number would be x by 3, right? And 5 more than x by 3 would be equal to x by 3 plus 5. So we have converted this statement over here into an equation with variables. Now we will see later more techniques to solve an equation. This is an introductory video. Now because I don't want you to be in suspense, let's quickly solve this, but we will see the methods in detail in future videos. Now x by 2 can be written as 3x by 6, right? If I multiply the numerator and the denominator with 3. Similarly, x by 3 can be written as 2x by 6 if I multiply the numerator and denominator with 2. So that's 3x by 6 and 2x by 6. Now I take this 2x by 6 to the left hand side of the equation. So that becomes 3x by 6 minus 2x by 6 is equal to 5. Now over here it's plus. When you change sides, the sign has to change. We'll see this in detail in future videos. So this is x by 6 is equal to 5 and that gives me x is equal to 30. So using this variable, we are able to find the number which we did not know. Now let's try to substitute it over here. What is x by 2? That's 15, right? What is x by 3? That is 10. And you can see that 15 is equal to 10 plus 5 and it satisfies the condition given over here. All right. Now let's see a few sample situations where using a variable is of great use. All right. So we have words and variables. That's the two things that we are trying to convert to. Now, in words, say a situation is mentioned as Bob is 5 years older than John. How do we convert that to variables? We take the age of John as X years, then the age of Bob would be X plus 5 years, right? Now let's take another situation. Mary got twice the marks Andy got. So how do we convert that to variables? Let's take Andy's mark as Y. Now it's given that Mary got twice the marks of Andy. So Mary would have got 2Y marks, right? Now you could do it the reverse way also. If you take Mary's marks as X, then Andy's marks would be X by 2, right? So both are right. All right. Now let's take one more situation. Rice costs $2 per kilogram. Wheat costs $3 per kilogram. Andy spent $20 buying rice and wheat. So how do we convert this into variables? Let's take that Andy bought X kilograms of rice and Y kilograms of wheat. So these are variables, right? Now we know that the cost of rice is $2 per kilogram. So for X kilogram, it will cost him 2 into X dollars, right? Now the cost of wheat is $3 per kilogram. So for Y kilogram, it will cost him 3 into Y dollars. Now he spent a total of $20. So 20 is equal to 2x plus 3y, right? Let me write that over here. 2x plus 3y is equal to 20. That's the total cost, right? Now in this manner, we can use variables to convert statements into expressions which we can solve for. Say you're given a number and you're asked to check whether that number is a prime number or not. Let's see how we can solve this type of problems. For this, we need to remember that factors of a number occur in pairs. Now, what do I mean with that? Say, let's take the number 6. Now, I know that 6 is equal to 2 into 3, right? Now, if I say that 2 is a factor of 6, along with 2, I also get 3, right? Because when you divide 6 by 2, you get your quotient as 3 and your remainder is 0. This indicates that if I divide 6 by 3, I will get the quotient 2 and the remainder is 0, right? Therefore, I can see that factors occur in pairs. All right. Now, using this concept, say you're asked to check whether 47 is a prime number or not. For this, there is an easy method that you can employ. Find the next higher number that is a square number. Over here we have 47. Let's do some trial and error. 6 square is 36. So that's not greater than 47. So let me try another one. 7 into 7, that's 49, and 49 is greater than 47. So 7 works. All right. Now you only need to check prime numbers up to 7 to check whether 47 is a prime number or not. What are the prime numbers up to 7? You have 2, 3, 5 and 7. So you just need to check whether 47 can be divided perfectly by 2 or 3 or 5 or 7. And you will see that 47 cannot be perfectly divided by any of these 4 numbers, and therefore, yes, 47 is a prime number. Now, let me also tell you one interesting thing about prime numbers. Always remember this, any prime number is of the form 6k plus or minus 1. What do I mean with that? Let's take our example over here. We have 47, right? Let's see whether this is of the form 6k plus or minus 1. Now, I can see that 47 can be written as 6 into 8 minus 1. 6 into 8 is 48. 48 minus 1 is 47. Therefore, you can remember this. This is an interesting property which can help you in many different types of situations. Any prime number is of the form 6k plus or minus 1. But at the same time, remember that any number which can be expressed as 6k plus or minus 1 is not necessarily a prime number. Alright. So it's just one way if you can find out that a number is not of the form 6k plus or minus 1, directly you can conclude that that number is not a prime number. But given that a number is of this form is not a sufficient enough condition, that's why we need to employ this method which we discussed over here. Now let's quickly try to solve two problems to establish what we have learned in this section. We are given two numbers and we are asked to check whether they are prime numbers or not. Now when it comes to checking the divisibility of a number by 2, 3, etc., do remember to check the divisibility rules section and you will get some easy tricks to find whether 2 or 3 or any of these numbers divides perfectly a given number. Now let's try to solve this problem only with the concepts that we have discussed so far. Let's take 783. Let me check if whether this is of the form 6k plus or minus 1. So 783 divided by 6 gives me a quotient of 130 and I'm left with a remainder of 3, right? If I do this normal division, this is my quotient and I get a remainder 3. Therefore 783 is not of the form 6k plus or minus 1 and hence it's not a prime number. Alright, let's try 143. If I divide 143 by 6, I'll get 23 as the quotient and my remainder would be 5. So this implies that I can write 143 as 6 into 23 plus 5, right? Try to do this along with me. Pause the video and keep working along with me. Now 6 into 23 plus 5 is one way of writing 143. I can also write it as 6 into 24 minus 1, right? What did I do? Here I had 23. I took the next number, that's 24, and I have a negative remainder over here. So that's an interesting concept. You can note that a remainder of 5 or a remainder of minus 1 actually means the same in case with respect to reminders. Now let's keep this aside and you can see over here 143 is of the form 6k minus 1. So the first criteria is satisfied. Now we have discussed that this alone is not enough to establish 143 to be a prime number. If this was not the case, if 143 was not of the form 6k plus or minus 1, we could have eliminated 143 from being a prime number. But now as that condition is satisfied, let's check using the method that we discussed before whether 143 is a prime number. So the first step is identify the next higher square number, and we know that 12 square is equal to 144. Therefore you need to check primes up to 12. You need to check whether those numbers will divide 143 or not. Now what are the prime numbers up to 12? The prime numbers up to 12 are 2, 3, 5, 7 and 11. So you have these 5 prime numbers, and when you check whether 143 is divisible by each of these, you will see that 143 divided by 2 gives you a remainder 1. So it's not divisible by 2. If you do 143 by 3, right, you will get 14 by 3, that's 4, it goes 4 times, you get a remainder 2, and you add 3 to it, that's 23 by 3, it goes 7 times, you get 21 and your remainder is 2, right? In a similar manner, you will see that 143 cannot be divided by 5 and 7, and we have already seen that 2 and 3 are not dividing perfectly 143. But when it comes to 11, if you do 143 divided by 11, you will see that first you take 14 by 11, it goes 1 time, your remainder is 3, and you take this 3 along with it, so 33 by 11, that's 3. So yes, 143 is perfectly divisible by 11. Therefore we conclude that 143 is not a prime number. We know what we mean with prime factorization. Let's practice what we learned and try to do these two questions. Let's start with prime factorizing 288. Alright, so we know the first step is write 288 and take out factor 2. That's because 2 is a factor that you can take out. So you're left with 144. Taking out a factor 2 means dividing 288 by 2, right? Now, what is a factor that you can take out from 144? You can see that you can take out 2, because 144 by 2 is 72. So let me take out 2 and I'm left with 72. Let me again take out 2 and I'm left with 36. Now 36 is also a multiple of 2. Let me again take out 2. I'm left with 18. I take out 2 again. I'm left with 9. And 9, from 9 I can take out 3 and I'm left with 3, right? Either I can leave it at this place because this 3 is a prime number, or I can take out 3 and write it as 1. So I leave it over here. Now I know that 288 is nothing but if I multiply all these numbers, right? I can say 288 is equal to 2 into 2 into 2 into 2 into 2. That's 5 2's, because you have 1, 2, 3, 4, 5. 5 2's over here, and you have 2 3's over here, because you have 2 3's over here. Now this can also be written as 2 to the power 5 into 3 to the power 2. You have 5 2's over here, that's why you have a power 5 over here, and you have 2 3's over here, that's why you have power 2 over here. Now let's try factorizing 512. We can take out 2 and we are left with 256. Let me again take out 2. I get 128 over here. I can again take out 2. I get 64 over here. Let me take out 2 again. I get 32 over here. Again I can take out 2. That leaves me with 16. Let me again take out 2. That leaves me with 8. And 8 by 2 is 4. And 4 by 2 is 2. And I can leave it at this place because this 2 over here is a prime number. Now the form of writing 512 in its prime factorized form is multiplying all these factors which we have taken out. And remember, all of these are prime numbers. That's why we call it as prime factorization. Therefore I can say 512 is equal to 2 into 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 2. That's 9 2's, or you can write it as 2 to the power 9. Now remember to check the section on divisibility rules. That will help you decide quickly what factor you can take out in each of these steps. Hi students, let's try to understand what we mean with HCF or GCD. HCF can be expanded as highest common factor, and GCD stands for greatest common divisor. We know that factor or a divisor is the same thing. It's a number that divides the given number perfectly, that is without leaving any remainder. Now let's try to understand what exactly this means. Say I have two numbers 12 and 16. Now let's try to find the HCF of 12 and 16. Let me write all the factors of 12. Now we remember that factors occur in pairs. So I can write 12 as 1 into 12. I can write it as 2 into 6. And I can write 12 as 3 into 4, right? Anything more than that, like I can write it as 4 into 3 also, but that would be a repetition of 3 into 4. So at this point we stop. Similarly, 16 can be written as 1 into 16, 2 into 8. There's no way of writing 16 as 3 into something, so that's not there. And I can write 16 as 4 into 4. Now from this I know that the factors of 12 are 1, 2, 3, 4, 6 and 12, right? That's all these numbers. 1 over here and I have 1 over here. I have 2 over here and I have 2 over here. Similarly, I have 3 over here. That's my 3 over here. 4 is here. That's 4 over here. 6 is over here. That's 6 over here. And 12 is here. That's 12 over here. So these are the factors of 12. Similarly, the factors of 16 are 1, 2, 4, 8 and 16. Now over here you can see that we need to find the highest or the greatest common factor, right? So what are the common factors in both the cases? We have 1 over here and 1 over here, 2 over here, 2 over here, and 4 over here and 4 over here. Among these common factors, which is the highest common factor? you can see that 4 is the highest common factor. Therefore, the HCF or the GCD of 12 and 16 is 4. Now, we have understood the meaning of HCF by trying to find the HCF of 12 and 16 in this manner. But this is a tedious manner. Let's see an interesting method to find the HCF of 12 and 16. So write the numbers like this and take out any common factor you can take out from 12 and 16. So I can take out 2. Taking out 2 means dividing 12 and 16 by 2 respectively. So 12 by 2 is 6 and similarly 16 by 2 is 8, right? Now is there any other common factor that I can take out? Yes, I can take out 2, right? So 6 by 2 is 3. Similarly 8 by 2 is 4. Now my HCF is multiplying these two numbers over here. That's 2 into 2, which is 4. And that's the same thing that we got over here. Now let's see one more method to find the HCF. Say I can write 12 as 2 into 2 into 3. That's the prime factorization of 12. Similarly, the prime factorization of 16 will give me 16 is equal to 2 into 2 into 2 into 2. Now just take the common factors out. So I have 2 into 2 common in both 12 and 16 over here. Therefore, I take it out and my HCF is 2 into 2, which is equal to 4. Now we know what HCF is. Let's try to learn what we mean with LCM. Alright, LCM stands for lowest common multiple. Let's try to understand this by taking an example. Let's take two numbers 12 and 18 and let's try to find the LCM of 12 and 18. For this, let me start with writing all the multiples of 12. That is 12 into 1 is 12, 12 into 2 is 24, 12 into 3 is 36, 12 into 4 is 48, and the multiples go on like that. Now let me write also the multiples of 18. 18 into 1 is 18, into 2 is 36, into 3 is 54, and it goes on like that. Now if we look at this expanded form of LCM, you can see that we need to find a common multiple. That is, we need to find a number that's occurring in this list as well as in this list over here. And it is mentioned that the number we find should be the lowest such common multiple, right? Now, what is the common multiple that you can see over here among these two? You can see that 36 is here as well as here, and that's the lowest common multiple. Therefore, the LCM of 12 and 18 is equal to 36. Now, we have understood what we mean with LCM using this illustration. Now, let's learn a method which will be commonly used whenever you need to find the LCM. Let me write the two numbers 12 and 18 over here. Now, take out any common factor among 12 and 18. So, I can take out 2, for example. So, 12 by 2 will give me 6 and 18 by 2 will give me 9. Now among 6 and 9, what is the common factor that I can take out? I can take out 3, right? 6 by 3 is 2, 9 by 3 gives me 3. Now the LCM is obtained by multiplying all these numbers. That's 2 into 3 into 2 into 3. That's 6 into 6, which is 36. Alright. Now if you had 3 numbers over here, say you are finding the LCM of 12, 18 and 25, right? You can still take out any common factor which occurs at least for 2 of the 3 numbers. For example, you can take out 2 in this case because 12 and 18 has a factor of 2. So let me take out 2 over here. That gives me 6 over here, and over here it gives me 9, and I have 25 over here. Let me take out 3 over here because in the case of 6 and 9, 3 is a factor. So if I take out 3, I have 2 over here, 3 over here, and 25 over here, and I have nothing else left to take out from this part. So the LCM in this case will be 2 into 3 into 2 into 3 into 25. Alright, now we will practice this more in a future video, but this is just for your understanding. Let's go on where we left off. We have seen one method to find the LCM over here. Now let's discuss one more method when we think of LCM using prime factorization. So I can write 12 as 2 into 2 into 3 in its prime factorized form. Similarly, I can write 18 as 2 into 3 into 3, right? Now, I have a 2 over here and a 2 over here. So I take out 1 2 and these two 2's are considered already. Now, similarly, I have 1 3 over here and 1 3 over here. So I write 1 3 over here and these two 3's are also considered. Now, I have a 2 over here. So I take it down, even though there is no 2 in the case of the prime factorization of 18 that is left, that's not already taken. I take out this 2 over here, and for this 3 I write a 3 over here, and I multiply all of these and I get my LCM as 36, which is the same value we got over here. Let's practice some HCF and LCM questions. Let's try to do the HCF of 28, 42 and 70. Now, what is a common factor that we can take out of them? I can take out 2, right? So 28 by 2 is 14, 42 by 2 is 21, and 70 by 2 gives me 35. Now, from 14, 21 and 35, is there any common factor that I can take out? Yes, I can take out 7, right? If I take out 7, I'm left with 2, 3 and 5. Now, from 2, 3, 5, is there anything that I can take out, any common factor? No, except from 1, there's no other common factor among 2, 3 and 5. Therefore, my HCF is 2 into 7, which is 14. Now, an interesting thing to note over here is you can write each of these as a multiple of your highest common factor, which is 14. So 28 is 2 into 14, 42 is 3 into 14, and 70 is 5 into 14, and that's expected because as it says in the word HCF itself, 14 has to be a common factor. That's why you see 14 over here, here and here. It's a common factor and it's the highest common factor among 28, 42 and 70. Alright, now let's find the LCM of the same numbers. This will give us a clear picture how HCF and LCM differ from each other. Now again, the first step is write the numbers and take out any common factor. So let me take out 2 again. So I'm left with 14, 21 and 35. Again, I can take out 7. I'm left with 2, 3 and 5. And among 2, 3, 5, there is no more common factor which I can take out. And therefore I stop over here. And my LCM is the product of all these numbers. That is, the LCM is equal to 2 into 7 into 2 into 3 into 5, and you will get that as 420. Now, as it says in the word LCM, 420 is a multiple of 28, 42 and 70. Let's observe. You can write 420 as 28 into 15 or 42 into 10 or 70 into 6. Therefore, it's a multiple of 28, 42 and 70, and it is the least common multiple. That's why it's the LCM of 28, 42 and 70. Alright, now let's try to find the LCM of 25, 15 and 21. Pause the video and give it a try. Alright, we start by writing the numbers and finding what the common factor I can take out, right? Now over here you will see that among these three numbers, there is no common factor for all the three, right? Therefore, the HCF would be 1 because you are not able to take out any common factor, right? But when you find the LCM, even if among two numbers, if there is a common factor, you can take that out. And you can see that among 25 and 15, you have 5 as a factor. So let me take out 5. So over here, 25 by 5 is 5, 15 by 5 is 3. And 21 is not exactly divided by 5, or 5 is not a factor of 21. Therefore, we write 21 as 21 itself over here. Now, among 5, 3 and 21, is there any common factor that I can take out? No, there is no common factor for all the three. But among 3 and 21, I can see that I can take out 3, right? So let me take out 3, and 5 cannot be divided perfectly by 3, so I write 5 as 5 itself. 3 divided by 3 is 1 and 21 divided by 3 is 7. Now there is no more common factor even among two of these three numbers that I can take out. So therefore I stop at this point, and my LCM is the product of all these numbers over here. That is, my LCM is 5 into 3 into 5 into 7. And remember, over here the HCF is 1 among 25, 15 and 21, because there is no common factor that I can take out among these three numbers. Let's do this problem. A merchant has 120 liters of oil of one kind, 180 liters of another kind and 240 liters of a third kind. He wants to sell the oil by filling the three kinds of oil in tins of equal capacity. What should be the greatest capacity of such a tin? Pause the video, give it a try, and then let's solve it together. Alright, so over here I have 120 liters of one type of oil, 180 liters of the other type, right? And 240 liters of the third kind. Now I need to fill this into tins, right? So this 120 liters has to be filled into tins. Say I need A tins for that. Similarly, 180 liters has to be filled into B tins, and 240 liters has to be filled into C tins. Alright, now given that all of these tins are of equal capacity, let's assume that the capacity of one tin is X liters. Alright, now what does that mean? If I am using A tins and each tin is of capacity X liter and it adds up to 120 liters, I can say 120 is equal to A into X, right? In a similar manner, I can say 180 is equal to B into X and 240 is equal to C into X. Alright, now you can see that in the case of 120, 180 and 240, X is occurring when you write it as a product of two numbers. So you can say that X is a common factor of both 120, 180 and 240. So we have established that X, that is the capacity of the tin, is a common factor among 120, 180 and 240. Alright. Now it's also mentioned that the capacity of the tin should be the greatest possible capacity. Therefore, the question deals with the highest common factor, which is HCF, right? We have seen that it deals with the common factor, and because the question says greatest capacity, it deals with the highest common factor or the greatest common divisor. Alright, now let's find the HCF of 120, 180 and 240. So we write the numbers like this and take out common factors. I have a 0, 0 over here, 0 over here. So I take out 10. So I'm left with 12, 18 and 24. I take out 6. 12 by 6 is 2. 18 by 6 is 3. And 24 by 6 is 4. And there's nothing more. There's no common factor among 2, 3 and 4 except 1 which I can take out. Therefore, I stop at this point. And the HCF is 10 into 6. That is 60. And that's the answer. 60 liters is the capacity of the tin. Let's do this question. Three brands A, B and C of biscuits are available in packets of 12, 15 and 21 biscuits respectively. If a shopkeeper wants to buy an equal number of biscuits of each brand, what is the minimum number of packets of each brand he should buy? Alright, pause the video, give it a try, and then we'll do it together. Alright, we are back. So what is given in the question? You have three types of biscuits, A, B and C. In one packet of A, you have 12 biscuits. Similarly, in one packet of B, you have 15 biscuits. And in one packet of C, you have 21 biscuits. So anybody who shops from over here can either buy 12, 24 or 36, etc. number of biscuits of type A. Why is that? Because you can only buy biscuits of type A in packets. If you buy one packet, you buy 12 biscuits. If you buy two packets, you buy 24 biscuits, and etc. Similarly, when it comes to biscuits of type B, you can either buy 15 biscuits, 30 biscuits, or 45 biscuits, etc. And with respect to biscuits of type C, you can buy 21 biscuits, 42, 63, etc. Now, it said that this person wants to buy an equal number of biscuits of type A, B, and C. So, whatever is the number of biscuits that he's going to buy, it should be part of this set of numbers, it should be part of this set of numbers, and it should be part of this set of numbers. We have seen that this is multiples of 12, this is multiples of 15, and this is multiples of 21. Therefore, we are looking at finding a common multiple of 12, 15, and 21. Now, given that he wants to buy the minimum number of packets, we need to find the least common multiple, because if we find a higher common multiple, he'll have to buy more number of packets. Alright, let's find the LCM of 12, 15, and 21. We write the numbers. 3 is a common factor of 12, 15, and 21, so I take it out. 12 by 3 is 4, 15 by 3 is 5, and 21 by 3 is 7. Therefore, my LCM is equal to 3 into 4 into 5 into 7. That's 420, right? 3 into 4 is 12. 5 into 7 is 35. 12 into 35. If you do the math, you'll get it as 420. Now, remember, we are not at the end of the problem yet, because the question does not talk about the number of biscuits he buys, but the number of packets of each brand. Therefore, if he has to get 420 biscuits of type A, and in each packet you have 12 biscuits, he has to buy 420 divided by 12, that is 35 packets of type A, right? Similarly, when it comes to biscuits of type B, he has to buy 420 by 15, that's 28 packets. And biscuits of type C, that's 420 by 21, or you get 20 packets. Therefore, the answer is that he has to buy 35 packets of type A, 28 packets of type B, and 20 packets of type C. Remember, if the question did not ask us about the minimum number of packets, even if he bought 70, 56, and 40 packets, still he would end up buying the same number of biscuits of each of the three types. We know what HCF is and we know what LCM is. We have already discussed how to find the HCF and LCM of a given set of numbers. Now, let's discuss how to find the HCF and LCM of fractions. Let's start with HCF. If you want to find the HCF of fractions, that would be equal to the HCF of the numerators divided by the LCM of the denominators. Let's take an example to understand this. Say you want to find the HCF of 1 by 2, 2 by 3, and 7 by 3. As per this formula, this would be equal to the HCF of 1, 2, and 7, that's the numerators, divided by the LCM of 2, 3, and 3. And this would be HCF of 1, 2, and 7 is 1, because there is no common factor among 1, 2, and 7. And the LCM of 2, 3, and 3 would be 6, right? You can take out 3, you will be left out with 2, 1, 1, and then 3 into 2 into 1 into 1 will give you 6, right? Therefore, the answer over here is 1 by 6. Remember, fractions have to be simplified for this to work. For example, if you are given a fraction 2 by 4, you need to write it as 1 by 2, right? 2 by 4 and 1 by 2 is the same value, right? There is a common factor 2 in the numerator and denominator. If you take that out, you are getting 1 by 2. So fractions need to be written in their simplified form for this to work. We'll deal more with fractions in the section on fractions. But remember, when you find the HCF of fractions, maintain every given fraction in their simplified form. Alright, let's find out the LCM of fractions. The LCM of fractions would be the LCM of the numerators divided by the HCF of the denominators. There's an interesting thing that you can note over here. When we try to find the HCF of fractions, that's HCF over here, we had HCF in the numerator and LCM in the denominator. Now, can you see the pattern over here? when you're trying to find the LCM of fractions, you have the same thing, LCM in the numerator and the other thing, HCF in the denominator. Alright, that's an interesting pattern so that you don't forget this formula. Let's do an example to understand this better. Let's say you want to find the LCM of 1 by 2, 2 by 3 and 7 by 6. This would be equal to the LCM of 1 to 7 divided by the HCF of 2, 3 and 6. 2, 3 and 6 are in the denominator, 1, 2 and 7 are in the numerator. Now, the LCM of 1, 2 and 7 will be 14. There is no common factor among them. So, you just multiply them, you get 14 over here, and over here you have denominator as 1 because 2, 3 and 6 have no common factor. So the highest common factor is 1 because 1 is a factor of every number. In this section, let's try to learn about the different types of fractions. So what are proper fractions? Let's take a few examples. Say 2 by 3 or 7 by 9. These are all proper fractions. You can see that in these cases, the numerator is less than the denominator. So you'll see that 2 is less than 3, 7 is less than 9. These type of fractions are called proper fractions. And you'll note that in the case of proper fractions, the value you get will be less than 1. Over here, you can see that 2 by 3 is less than 1. It's 0.666. That's less than 1, right? Alright, let's move on. Improper fractions are fractions such as 7 by 4 or 9 by 7. Over here, you can note that the numerator is greater than the denominator. And the value of improper fractions will be greater than 1. 7 by 4 is greater than 1, right? 4 by 4 will be equal to 1 and 7 by 4 is equal to 1 plus 3 by 4 or 1.75, which is greater than 1. Alright, let's move on. The next type of term that we need to learn is mixed fraction. Mixed fractions are numbers of the form, for example, 2, 4 by 5. And if you have an expression 2, 4 by 5, that means 2 plus 4 by 5. Now, this type of expressing of fractions is called mixed fractions, where you have a whole part and you have a fraction. Now, let's see how we can convert a mixed fraction into an improper fraction. I can write 2 as 2 by 1, right? 2 is the same as 2 by 1, and I can multiply the numerator and denominator with the same number. So 2 is nothing but 10 by 5. Therefore, if I replace 2 with 10 by 5, I can write 2 plus 4 by 5 as 10 by 5 plus 4 by 5. So I add the numerators and I keep the denominator the same. So that is equal to 14 by 5. So 2 4 by 5 can also be written as 14 by 5. And you can note that 14 by 5 is an improper fraction. Alright. Now, say you were initially given 14 by 5 and you have to convert it to a mixed fraction. Let's see how you can do that. So the way of that is simple division. So let me divide 14 by 5. So over here, when I do 14 divided by 5, it goes 2 times. I get 10 and I get a remainder of 4, right? So my quotient 2 comes over here. That's the whole part. And I have a remainder of 4. That's what comes over here. And the divisor is 5. That's over here. This is the way in which I can convert an improper fraction into a mixed fraction. Alright, the next term that we learn over here is equivalent fractions. Say you have a fraction 1 by 2. If you multiply the numerator and denominator with the same number, you will get an equivalent fraction. So I have 1 by 2. Let me multiply the numerator and denominator with 5. So I get 5 by 10. Now 1 by 2 and 5 by 10 are both equal to 0.5. So both are equal, right? So I can see that one fraction can have an infinite number of ways of expressing it. For example, 5 by 10 can also be written as 10 by 20 or 100 by 200, right? Alright, so we have seen one way of arriving at an equivalent fraction is to multiply the numerator and denominator with the same number. It's not only multiplication, you could also divide the numerator and denominator with the same number. Say you have 10 by 24. Let's divide the numerator and denominator with 2 and I get 5 by 12. Now 10 by 24 and 5 by 12 are the same value. So to get an equivalent fraction, I either multiply or divide both the numerator and denominator with the same number. In this video, let's learn how to add and subtract fractions. Say you want to add 2 by 3 and 4 by 5, right? Over here, you can see that you have 3 in the denominator over here and you have 5 in the denominator over here, and these are not equal. So the method of going about this is convert these into equivalent fractions such that they have the same denominator. So let's find what I should change 3 into and what I should change 5 into. For that, let's find the LCM of 3 and 5. The LCM of 3 and 5 is 15. So for that matter, I could have taken any common multiple of 3 and 5. It's just easy to work with the LCM. That's why we are taking the least common multiple, which is 15. Now, if I want to change this 3 into 15, I need to multiply this 3 with 5. So I need to multiply the numerator as well with 5. So I get 2 by 3 into 5 by 5, right? And if I want to change this 5 into 15, I need to multiply it with 3, and then I need to multiply the numerator, that is 4, also with 3. So my addition problem becomes 2 into 5 by 3 into 5 plus 4 into 3 by 5 into 3. Now the denominators are the same. Over here I have 15 and over here I have 15. When you are trying to add two fractions and if the denominator is the same, all you need to do is add the numerators and keep the denominator as it is. Therefore, the answer over here is 10 plus 12 by 15, which is 22 by 15. Alright, now let's go on to subtraction of fractions. Say I want to do 7 by 9 minus 1 by 2. The method is the same. You need to convert them into fractions that have the same denominator. Let me find the LCM of 9 and 2. That's equal to 18 because there's no common factor among 9 and 2. So I just need to multiply 9 and 2 and that's 18, right? That would be like, say, with the method that we learned, I write 9 and 2. I take out 9. I write 1 over here. 2 is not perfectly divided by 9. So I just keep 2 over here. Again, I take out 2. I keep 1 over here because 1 is not perfectly divided by 2 and 2 by 2 is 1. So 9 into 2 into 1 into 1, that's same as 9 into 2, which is 18. Now, let me convert these into fractions which have 18 in the denominator. So I can write 7 into 2 by 9 into 2 minus 1 into 9 by 2 into 9. Now you have the same denominator in both these cases. When you are trying to do subtraction of fractions and you have the same denominator, just do the operation on the numerator and keep the denominator as it is. So that's equal to 14 minus 9 by 18, which is equal to 5 by 18. Let's learn how to compare fractions and find which among the two given fractions is the bigger value. Say you want to compare 3 by 4 and 5 by 6. And you want to find which among these two is the greater fraction. Now, to do this, you need to make them into like fractions. So, like fractions are fractions with the same denominator. It's the same method that we followed for addition and subtraction of fractions. Let's find the LCM of 4 and 6. The LCM of 4 and 6 can be found out like this. You write 4 and 6 and take out the common factor. So 2 is a common factor. So I am left 4 by 2 is 2, 6 by 2 is 3. Now, therefore my LCM is 2 into 2 into 3, which is 12. Now, 3 by 4 has to be written as an equivalent fraction with 12 in the denominator. So I can do that by multiplying the numerator and denominator with 3, and I get 9 by 12. Similarly, 5 by 6 can be multiplied with 2 in the numerator and denominator, and I get 10 by 12 as the equivalent fraction. Now, when I want to compare 9 by 12 and 10 by 12, because both of these have the same denominator, I just need to compare 9 and 10. Therefore, 9 by 12 is less than 10 by 12, and because of this, 3 by 4 is less than 5 by 6. Let's discuss multiplication and division of fractions. Say you want to multiply 7 by 13 with 3 by 5. All you need to do is multiply the numerators and you get the numerator, multiply the denominators and you get your denominator. So the answer will have a numerator of 7 into 3, which is 21, and the denominator is 13 into 5, which is 65. So 7 by 13 into 3 by 5 is equal to 21 by 65. Alright, let's try a division problem. If you want to do 2 by 5 divided by 3 by 7, right? In this case, instead of dividing with 3 by 7, you can multiply with the inverse of 3 by 7. The inverse of 3 by 7, let me write that over here, will be 7 by 3. So you interchange the numerator and the denominator and you get the inverse. So instead of dividing with 3 by 7, you can multiply with 7 by 3. So I can write this as 2 by 5 into 7 by 3. And then I apply what we learned over here. This is equal to 14 by 15. 2 into 7 gives me 14. 5 into 3 gives me 15. Now, there's one more interesting way of thinking about this. Division can be thought of as putting something in the denominator, right? Remember, 2 by 5 is nothing but 2 divided by 5, right? So therefore, 2 by 5 divided by 3 by 7 would be 2 by 5, and you put 3 by 7 in the denominator, right? Just like you put 5 over here when you have divided by 5. Now, over here, when you get an expression like this, and remember it's the same thing that we have solved over here, you can see when you compare these two that you have the 3 over here and you have the 3 over here. This 7 has to go to the numerator. So this is equal to 2 into 7 divided by 5 into 3. So this 7 goes up, right? And then that's 14 by 15. So if you have another expression, say 2 divided by 3 divided by 7, over here in this case this 7 goes up. So this is equal to 2 into 7 divided by 3, which is 14 by 3. Let's try to brush up our knowledge on decimals. We start with understanding the expanded form of a decimal number. Say you have the number 278.325. Over here you have the decimal point. Let's identify the place values of each place or position of this number, right? So 8, the number 8 over here is at the ones place. The number 7 is at the tens place, and the number 2 is at the hundreds place. Alright, now what about the number 3? It's after the decimal point, and the place value where the number 3 is placed is tens, which comes from 1 by 10. Similarly, the place value of the digit 2 is hundreds, which corresponds to 1 by 100, and the place value where the number 5 over here is thousands, and it corresponds to 1 by 1000. Now let's write the expanded form of this number, and remember this number is written in base 10. Alright, the expanded form of a number is obtained when you multiply the digit with its place value. For example, you have to multiply 2 with 100, 7 with 10, 8 with 1, and you have to multiply 3 with 1 by 10, 2 with 1 by 100, and 5 with 1 by 1000. So the expanded form of this number is 2 into 100 plus 7 into 10 plus 8 into 1 plus 3 into 1 by 10 plus 2 into 1 by 100 plus 5 into 1 by 1000. Let's visit addition and subtraction of decimals in this video. Say you want to add 9.64 and 12.7. The point that you need to keep in mind when adding decimal values is you have to align the decimal points. So let's do that. So I have 9.64 over here and 12.7 over here, and you can see that the decimal point has been aligned. Now over here I have nothing. This is the same as having 0 over here, right? Because 12.7 is the same as 12.70, which is the same as 12.7000. I can add any number of zeros in the decimal position after the last provided decimal number, right? All right, so this is equal to 9.64 plus 12.70, and then you just add the numbers. 4 plus 0 is 4, 6 plus 7 is 13, you write 3, 1 is carry forward, 9 plus 1 is 10, plus 2 is 12, so 2, 1 carry forward, 1 plus 1 is 2, and this is your answer. Alright, let's try to do a subtraction involving decimal numbers. Say you want to do 7.63 minus 2.47. Again, the point to keep in mind over here is you have to align the decimal points. Let's do that. So I write it like this, and then you just subtract the numbers. So 13 minus 7 is 6. You gave 1 to 3, so you are just left with 5 over here. 5 minus 4 is 1. 7 minus 2 is 5. Remember to keep the decimal point just below where you have aligned it. So the decimal point over here is aligned, as you can see. And also do remember, in the case of subtraction, to maintain the correct order, because remember 7.63 minus 2.47 is not equal to 2.47 minus 7.63. Let's learn how to multiply decimal numbers. Say you want to do 3.5 into 2. The first step is do the multiplication as if there was no decimal number involved. So 35 into 2 we know is 70. Now to get to 35 from 3.5, you had to move the decimal point by one place to the right, right? Over here you have 3.5, the decimal point is over here, and for 35 is the same as 35.0, right? So you move the decimal point from here to here. That's one place to the right. So need to compensate for that and move the decimal point by one place to the left. So you do that like this, and your answer is 7.0. Say you want to do 2.34 into 3.12. The first step is do the multiplication as if no decimal point was involved. So you do 234 into 312. So that gives you 73,008. This is just normal multiplication, right? Now, after you get this answer, see what manipulation you had to do in the question to get to this. Over here, you can see that you moved the decimal point by two places to the right, to get to 234. Similarly, over here, you have moved the decimal point by two places to the right. So you have moved the decimal point by 4 places, 2 here and 2 here. So that's a total of 4 places to the right. To compensate for that, in the answer, currently the decimal point is over here, right? You need to move this decimal point by 4 places to the left. So when you do that, you get your answer as 7.3008, and that is your answer. Let's learn how to divide decimal numbers. Say you want to do this problem, 33.725 divided by 0.25. Alright, now the way to approach this is convert this into a division problem where no decimal point is involved, And to achieve that, you can multiply the numerator and denominator by the same number. So over here I can see I have 3 decimal places. Over here I have 2 decimal places. So if I multiply the numerator and denominator with 1000, this changes to 33725 divided by 250, right? Multiplying with 1000 moves the decimal point by 3 places to the right. So in the numerator becomes 33725. In a similar manner, I have to move the decimal point by 3 places to the right in the denominator, and that becomes 250. So you can see we have converted this into a normal division problem. Now let me cut 5 both from the numerator and denominator. So that's 6745 divided by 50 now. Again, I can see I can still take out 5 both from the numerator and denominator. Let me do that. So that becomes 1349 by 10, and this is my answer, 1349 by 10, which is nothing but 134.9. Let's do one more question. Say you want to do 25.7 divided by 1.25. In the numerator I have 1 decimal place, in the denominator I have 2 decimal places. So I can move the decimal point by the same number of places in the numerator and denominator, right? So by multiplying both the numerator and denominator with 100, this question changes to 2570 divided by 125. Now we have converted it into a normal division problem. Let me take out 5 both from the numerator and denominator, and this becomes 514 divided by 25. Now 514 divided by 25, it goes 2 times. Alright, I can also add zeros over here. I can write 514 as 514.000, right? It's the same value, does not change. Remember, 514 is equal to 514.00, right? Now using this I have added a few zeros, depends on what level of precision we want in the answer. Now 25, I have 51, that goes 2 times, so that's 51 remainder. Let me take down the 4. 25 will not go in 14, so that's 0 over here. Let me take down this 0. Now it's 140 over here. Because I've used a decimal place, right, value, I have to remember to put the decimal point in the quotient. So that's the decimal point over here. Now 140 by 25, it goes 5 times. That's 125, and I get a remainder of 15. Let me take down the next 0 over here, and 150 by 25, it goes 6 times, right, and I get a remainder of 0. So this is my answer. It's 20.56. Hi students, welcome to this next section where we are discussing classification of numbers. Say you have the numbers 1, 2, 3, etc. These are the natural numbers because they come naturally to us, and we call them as counting numbers or natural numbers. Now, if you add 0 to this set of numbers, we get the set of whole numbers. So the whole numbers are numbers starting from 0 and they go on 0, 1, 2, 3, etc. Now, if you add to this the negative numbers, you get the set of integers. So integers include negative numbers like -1, -2, -3, etc. Integers include 0, and integers include positive numbers like 1, 2, 3, 4, etc. Now, if you add to this fractions like 1 by 2, 1 by 3, or negative ratios like -4 by 3, -4 by 7, these are called rational numbers. So rational numbers include integers, whole numbers, natural numbers, all are part of rational numbers. So all of these numbers, whatever comes inside here, are rational numbers. Now, rational numbers are numbers which can be expressed in the form p by q, where p and q are integers and q is not equal to 0 because division by 0 is not defined. So you can note that 0 can be written as 0 by 1. This is of the form p by q where q is not equal to 0. Therefore 0 is also a rational number. Any negative number, say minus 2, it can be written as minus 2 by 1, which is of the form p by q, where q is not equal to 0. Therefore integers are also rational numbers, and any positive number also can be written in the form p by q. Say you have 2, you can write it as 2 by 1, or you can write it as 4 by 2, right? So all the natural numbers are also rational numbers. Now let's keep this set of rational numbers aside. There is another set of numbers which we call the set of irrational numbers. Some of the examples of irrational numbers are root 2, pi, root 3, or say this decimal number 0.122333, etc. We will soon see how you can identify when a number is given to you, whether it's a irrational number or a rational number. We'll soon see that. Now remember, irrational numbers are numbers which cannot be expressed in the form p by q, where p and q are integers and q is not equal to 0. Now irrational numbers and rational numbers together are called real numbers. Now that we know what rational numbers and irrational numbers are, let's try to think how we can identify whether a given number is a rational number or an irrational number. For this purpose, the decimal expansion of the given number will give us a clue. Let's analyze this. In the case of a rational number, the decimal expansion will either be a terminating decimal expansion or a non-terminating recurring decimal expansion. Now what do I mean with this? Let's try to understand this. Well, let's start with this one, a terminating decimal expansion. Say you have the rational number 3 by 4. If you divide 3 by 4, you will get 0.75. So this is the decimal expansion of 3 by 4, and you can see that this is terminating because it stops at this place. So it's exactly 0.75 and it stops, right? So it's a terminating decimal expansion. Now if you take the fraction 1 by 3, you will see that it's 0.333 and it keeps going on like this. It never ends. And we can write this type of a decimal expansion as 0.3 with a bar above the repeating part. So for example, let's take another example. 1 by 7 is 0.1428571428, and it goes on like that. So I can write this as 0.142857 with a bar on top, because this is the repeating part. It keeps repeating again and again in the decimal expansion. So you can see that these type of decimal expansions are non-terminating because they do not end, and they are recurring because they have a clear recurring part. Let's take one more example. Say you have 0.1232323. You can see that only 23 is getting repeated, right? 1 is not getting repeated. So this can be written as 0.123 with a bar on top of 23. Alright, so we have seen that any rational number, when you convert it to its decimal expansion, you will either get a terminating decimal expansion or a non-terminating recurring decimal expansion. Now let's analyze what happens in the case of an irrational number. In the case of an irrational number, the decimal expansion will be non-terminating and non-recurring. It will be non-terminating, that means it will never end, and it will not have any recurring part. Let's take an example. 0.01, 0011, 000111, etc. We can see that there is no set of digits in the decimal places that gets repeated again and again. So this is an example of an irrational number. Let's take a few more examples. Say you take root 2. The decimal expansion of root 2 is this one over here. You can see that there is no repeating set of digits, and it does not end. Similarly, the decimal expansion of pi is this one. It's 3.14159, etc. You can see there is no set of digits that gets repeated again and again in the decimal places, and it does not terminate. So you can see that for an irrational number, the decimal expansion will be non-terminating and non-recurring. There's an interesting side note over here. In many geometry problems, we approximate pi to 22 by 7, but pi is not 22 by 7 because it's an irrational number. It cannot be expressed in the form p by q, but taking pi as 22 by 7 is only an approximation. Now, let's quickly revise what we have learned. The property that we have learned is for a rational number, the decimal expansion will either be terminating or non-terminating and recurring. For an irrational number, the decimal expansion will always be non-terminating and non-recurring. Now, with these properties, when you are given a decimal expansion, you can clearly know whether it's a rational number or an irrational number. For example, if you are given this decimal expansion, you can see that it's non-terminating and non-recurring. Therefore, it has to be an irrational number. We have seen that every terminating decimal expression is a rational number, and we know that for rational numbers, they can be expressed in the form p by q, where p and q are integers and q is not equal to 0. So let's learn how to convert a terminating decimal expression to the form p by q. Let's take an example. Say you want to convert 4.7285 into the form p by q. So 4.7285 is the same as 4.7285 divided by 1, right? Now let me multiply the numerator and denominator with 10,000. So I get 4.7285 into 10,000 divided by 10,000. Now when I do this multiplication, I have to shift the decimal point by 4 places to the right, and that amounts to 47285 divided by 10,000. I can take out 5 both from the numerator and denominator, and it simplifies to 9457 divided by 2000. So I have successfully expressed this terminating decimal expression in the form p by q. Let's take one more example. Say you want to do 3.72 in the form p by q. Now I can multiply the numerator, and in this case the denominator is 1. I can multiply the numerator and denominator by 100. That gives me 372 by 100, and this is of the form p by q. In this video, let's learn how to express a non-terminating recurring decimal expression as a rational number. We have learned that a non-terminating recurring decimal expression is a rational number, and rational numbers can be expressed in the form p by q. So let's learn how to do this conversion. Let's take an example. Let's have 0.333 and it goes on like that, which is the same as 0.3 with a bar on top of 3. Now let me take x as 0.333, etc. Because only one digit is repeating, let me multiply both the sides of this equation with 10. That gives me 10x is equal to 3.33, etc. Now I can split 3.333, etc. as 3 plus 0.333, and this part over here is the same as x, which we have taken over here. Therefore this can be written as 3 plus x. Let me take x to the left hand side. So that becomes 10x minus x is equal to 3, or 9x is equal to 3, and therefore I have x is equal to 3 by 9. I have successfully expressed 0.3 bar in the form p by q. And if you want to check, you can do the division and you will see that you get 0.333, etc. Alright, let's do one more question. Now this is the longer method. Once we are very thorough with this, we will learn a shortcut to do this very quickly. Okay, let's move on. Say you want to do 0.345 with a bar on top of 4 and 5. You want to convert it into the form p by q. Now this is equal to 0.34545, etc. let that be equal to x. I have my x over here. Now over here you can see that two digits are repeating, right? Therefore I have to multiply the left hand side and the right hand side by 100. So that gives me 100x is equal to 34.5454 etc. Right? This can be written as 34.2 plus 0.345 with a bar on top of 45. Now, how do you determine that this has to be 34.2? It's actually engineered in a manner that you will get x over here, right? So to get this number, just subtract this much from this value over here. Let's do that over here. When you do that subtraction, when you subtract x from 34.5454 etc., you will get 34.2. Alright, so we have split this number as 34.2 plus 0.345 with a bar on top of 45. This is equal to 34.2 plus x. Let me take x to the left hand side. That becomes 99x is equal to 34.2. Let me multiply both the sides of the equation with 10. I get 990x is equal to 342, and therefore x is equal to 342 by 990. Let's learn a shortcut to express a non-terminating recurring decimal in the form p by q. Let's take this example. Say you want to convert 0.456 with a bar on top of 4, 5 and 6 into the form p by q. Over here you can see that the whole decimal part is repeating, right? So you write the whole decimal part as the numerator. You have 3 digits that are getting repeated over here. Therefore you write 3 nines in the denominator, and this is your answer. So you have 3 digits over here. That's why you have 3 nines over here. All the decimal section is getting repeated. So you write the whole decimal places in the numerator. So 0.456 with a bar is equal to 456 by 999. Let's do one more question. Say you want to do 0.3 bar. You can see that the whole decimal section is getting repeated. So you write that as the numerator. You have 1 digit that's getting repeated. That's why you write only 1 9 in the denominator, and 3 by 9 is the answer. What about 0.67 bar? That would be 67 divided by 99, because 2 digits are getting repeated in the decimal section, right? That's why you have 2 nines over here. Alright, now what about 0.66 bar? That would be 66 by 99. In all these cases, the whole decimal section was getting repeated. Let's take another example. What about 0.25735 with the bar only on top of 7, 3 and 5? That means only 735 gets repeated, right? So in this case, let's see how many digits are getting repeated. That's 3, right? Therefore, you write 3 nines in the denominator. Now, you have 2 digits that are not repeating, right? Therefore, you write 2 zeros over here. The next step is, in the numerator, write the whole decimal section over here. So that's 25735, and subtract the non-repeating part. This is the non-repeating part. So subtract the non-repeating part, that's minus 25. And this is your answer. The numerator you get 25710, and in the denominator you have 99900. And of course you can simplify this. For example, you can cut out 0 from here and here, but this is in the form p by q. Let's do one more question. If you want to do 0.12386 with the bar on top of 86, that would be equal to this much, right? You have 2 nines because 2 digits are repeating. There are 3 non-repeating digits over here, so you have 3 zeros. You write the whole decimal part over here, and you subtract the non-repeating part, which is 1, 2, 3. and if you do the calculation, your numerator will be 12263 and you have 99000 in your denominator, and this is of the form p by q. Now in all these sections we have seen numbers that started with 0 point, right? In all these problems, let's see a number that does not start with 0 point something. Say we know that 0.142857 bar is equal to 1 by 7. How do we find 3.142857 with a bar over here? Now I can write this as 3 plus 0.142857 bar, right? And I know that this much is equal to 1 by 7. So this is equal to 3 plus 1 by 7, which is 3 1 by 7. This is a mixed fraction. I can also write it as 3 into 7 plus 1, that's 22 by 7. Alright, now a fun fact, this 22 by 7 is what in many problems pi is approximated to, but pi is not equal to 22 by 7 because pi is an irrational number. This is only an approximation taken in many questions. Now just side fact, if you want to find 0.142857 bar in the form p by q, if this was not given, how would you approach it? You can see that the whole decimal section is getting repeated. So you have 1 2 3 4 5 6 digits that are repeated. So your answer would be 142857 divided by 6 nines. Let's do these two questions. The first question reads, what type of a number is 4 into pi? Pause the video and give it a try. Alright, we are back. Let's do it together. We know that pi is an irrational number, right? Therefore, 4 pi will also be irrational because it will have an irrational decimal part. Remember, the decimal expression of pi has a non-terminating, non-recurring decimal expression, right? Now, even if you multiply that decimal part with 4, you will get a non-terminating, non-recurring decimal part, and therefore 4 pi will be irrational. Let's do the next question. It's a true or false question. The question reads, any addition, subtraction, division or multiplication operation involving irrational numbers will result in an irrational number. So in the first question we have seen that we had a multiplication operation 4 into pi and we got the answer as irrational. Now the second statement is a true or false question, and it's generalizing that any addition, subtraction, division or multiplication operation involving an irrational number will give an irrational number. Pause the video, give it a try, and then let's do it together. Alright, we are back. Let's take an example. If I do pi minus pi, I get 0, and you can see that 0 is a rational number, right? Therefore, it's not always an irrational number that you get as the answer. Sometimes if you do pi minus 2, for example, you will get an irrational number. But you cannot say that you will get always an irrational number. Therefore, this statement over here is false. Let's take a few more examples. Root 2 into root 2, that's 2, right? Root 2 is an irrational number, but root 2 into root 2 will give you 2, which is a rational number. Root 2 divided by root 2 will give you 1, which is also a rational number. Minus root 2 plus root 2, that gives you 0. 0 is a rational number. So this statement is false. In some cases the answer would be irrational, and in some cases the answer is rational. In this video, let's learn about the importance of defining the order of operations. Let's see the need of defining the order of operations using an example. Here we have 4 plus 8 into 2. Say two people are there, Jim and Tom. Jim thinks, let me first do 4 plus 8 and multiply that with 2. So he gets 12 into 2, which is 24 as the answer. Now Tom thinks that let me do 8 into 2 first. So he gets 4 plus 16 and his answer is 20. Now for the same expression, there are two answers. So which is the correct answer? Here we have seen a typical example of the need to define the order of operations, whether addition has to be done first or multiplication has to be done first in this type of an expression. This is of utmost importance so that across the world, if anybody tries to do this problem, they should be getting the same answer. Here comes the importance of the BODMAS rule. Now, B stands for brackets, O stands for order of, D stands for division, M stands for multiplication, A stands for addition, and S stands for subtraction. This is the order of operations. Now, whenever you have an expression, you have to simplify the brackets first. Next comes order of. Order of is something that stands for power. Like for example, 2 into 2 into 2, that's 2 cube. So if you have something like 2 cube, that has to come in the second priority. Next one is division and multiplication. These two have the same order of priority. And then you have addition and subtraction, and these two also have the same priority. In the case of division and multiplication or addition and subtraction, you just need to do the operations from left to right. For example, if you have division and multiplication in the same expression, do the operations from left to right. Alright, now to understand these better, let's take a few examples and try to apply these rules. Now, the first one, over here you have addition and you have multiplication. From the BODMAS rule, we can see that division and multiplication come before addition and subtraction. Therefore, you have to do the multiplication over here first, and this becomes 4 plus 16, that is 20. Now, the next one, you have a bracket over here. The opening bracket is over here and the closing bracket is over here. As per the BODMAS rule, brackets need to be simplified first. So this becomes 12 into 2, which is 24. Now, in the next expression, we have division and multiplication. We have seen over here that these two have the same order of priority. Therefore, you need to do the operations from left to right. So you have to do 40 divided by 4 first. That gives you 10, and 10 into 5 is 50. See, if you had done it in the reverse manner, if you had done 4 into 5 first, you would have got 20 over here, and 40 by 20 is 2, which is a totally different answer from what you are getting over here. Now in the next one, you have subtraction and addition. So just do the operations from left to right, because addition and subtraction have the same priority. So this is equal to 5 plus 3 minus 1, which is 8 minus 1, which is 7. Now in this operation, you do the operations from left to right because you have two divisions. So 360 by 36, that gives you 10, and 10 divided by 2 gives you 5. Now if you had done it in the other order, if you had done 36 divided by 2 first, you would have got 18, and 360 divided by 18 is 20, which is a totally different answer. So this is the right answer. Remember, in these cases, you have to do the operation from left to right. Let's discuss the different types of brackets in expressions. So these are the 4 types of brackets that can occur in an expression. These 4 types are no different. There's not one that's more important than the other. The only thing that you need to keep in mind is open inner brackets first. Whenever you have multiple brackets in an expression, you have to open the inner brackets first. Say for example, you have this expression over here. Now 2 plus 3 is the innermost expression over here, right? Therefore you have to open that first. So this becomes 2 into 6 minus 5, which is 2 into 1. 6 minus 5 gives you 1, and that gives you the answer as 2. So open inner brackets first. Alright, now if all the brackets as we have stated here are no different, are of equal priority, why do you have these 4 types of brackets? The vinculum, simple brackets, curly brackets, and square brackets. So what's the need of these different types of brackets? Let's try to understand that. Over here, I have an expression. Now there are multiple brackets used and it's difficult to understand which opening bracket corresponds to which closing bracket. Of course, with a careful eye you can identify it. For example, this opening bracket corresponds to this closing bracket. So if you go from the inside to the outside with a careful eye, you can identify it, but it is difficult to read. Imagine I use different colors for the brackets. So now it becomes very easy. I can see that this bracket corresponds to this one, right? This opening bracket corresponds to this closing bracket, and so on and so forth. Now it's difficult to have these type of color coding when you write an expression, and instead of this we have these different types of brackets. So now easily I can see that this opening bracket corresponds to this closing bracket, this opening bracket corresponds to this closing bracket, this opening bracket corresponds to this one over here. Now let's try to solve it. Over here you have the vinculum, right? Now this is like 3 and 3 plus 4 is in a bracket, that's the vinculum. Now let's solve this first because it's the innermost bracket. This becomes 7 over here. Now the next innermost bracket is this part over here, right? So that's 1 plus 2 into 7, that's 15, right? So we write that over here like this. Now the next innermost bracket is this part over here. So you have 8 plus 4 into 15. 4 into 15 is 60. 8 plus 60 gives you 68. So we write this over here like this. We get 5 plus 2. 5 plus 2 plus 68. 2 plus 68 is 70. 5 plus 70 is 75, which is your answer. In this section, let's go through the various laws of exponents. Alright, let's take examples and go through each of these laws so that you will be able to easily remember them and apply them in any question. Say you have 2 to the power 1. That's nothing but 2 itself, and that's the law over here. Say you have 3 to the power 2 into 3 to the power 3. Now 3 to the power 2 is 3 into 3. Similarly, 3 to the power 3 is 3 into 3 into 3. Now when you multiply this, you have 5 3's. So this is equal to 3 to the power 5. And you can see that that was obtained as 3 to the power 2 plus 3. So that's the law over here. So you can note that in this case, the base is the same. This is called the base, right? And this is called the exponent. Let me write that over here. This is the exponent and this is the base. Now when you have the same base, you can just add the exponents. That's the law over here, right? Now let's try to do 3 to the power 4 divided by 3 to the power 2. Now I can write this as 3 into 3 into 3 into 3 divided by 3 into 3, right? Now I can cut the common factors in the numerator and denominator, and I am left with 3 into 3, which is 3 square, or 3 to the power 4 minus 2. Here also you can note that the base is the same. You have 3 as the base in this number and you have 3 as the base in this exponent. So the base is the same. So if you have a division operation to do and the base is the same, you keep the base as it is and subtract the exponents. Alright, that's the law over here. Let's go on. Say you want to do 3 to the power 2 divided by 3 to the power 2. That's 3 into 3 by 3 into 3. And the numerator and denominator is the same. So you get this as 1. And as per the law that we learned over here, this can be written as 3 to the power 2 minus 2, right? Because the base is the same. So let me write it as 3 to the power 2 minus 2, which is equal to 3 to the power 0. Therefore, a to the power 0 is equal to 1. Now this is applicable when a is not equal to 0, because 0 to the power 0 is not defined. Let's move on. Say you want to find 3 to the power minus 2. Now I can write minus 2 as 0 minus 2, right? 0 minus 2 is equal to minus 2. When I want to do 3 to the power 0 minus 2, based on this law that we learned over here, I can write this as 3 to the power 0 divided by 3 to the power 2, right? And based on what we learned over here, I know that 3 to the power 0 is nothing but 1. Therefore, this expression over here becomes 1 divided by 3 to the power 2. That's what we learn over here. A to the power minus n is nothing but 1 by a to the power n. Alright, 3 to the power minus 2 is equal to 1 by 3 to the power 2. Alright, now let's go to the next law. Say you want to do 2 cube the whole square. Now that is equal to 2 cube into 2 cube. Over here you can see that the base is the same. Based on this law, the first one over here, I can see a to the power m into a to the power n is equal to a to the power m plus n. So over here I will get 2 to the power 3 plus 3 or 2 to the power 6. And you can note that this 6 can also be obtained as 2 to the power 3 into 2. So when you have a to the power m to the power n, that's equal to a to the power m into n. Alright. Now the next one is, say you want to do a to the power m into b to the power m. Alright. Let's take an example. 2 square into 3 square. You can see that the base is different. Over here the base is 2. Over here the base is 3. The base is different, but the exponents are the same. In this case, let's try to understand why we can write it like this. Let me expand it. This is 2 into 2 into 3 into 3. And let me club it like this. 2 into 3 into 2 into 3. Now this is equal to 2 into 3 the whole square, right? 2 into 3 is getting repeated 2 times. You're multiplying it. Therefore, I can write it as 2 into 3 the whole square. And that's why when you have the same exponent but different bases, you can club the base together and keep the same exponent. So a to the power m into b to the power m is equal to ab to the power m. And the same law holds for division as well. If you have 2 square divided by 3 square, that is equal to 2 by 3 the whole square. We have discussed the laws of exponents, and in these laws, these exponents can be any real number. So they can be natural numbers, 0, or they can be negative numbers. They can be rational numbers or irrational numbers. Let's try to see how negative numbers fit in these laws. Let's try to do 2 to the power minus 3 into 2 to the power minus 4. Now you can see that the base in both these numbers is the same. You have 2 over here and you have 2 over here. So it's similar to this rule that we have seen before, and this simplifies to 2 to the power minus 3 plus minus 4, which is equal to 2 to the power minus 7. Alright, now let's try to think of it. 2 to the power minus 3 as per this rule is equal to 1 by 2 to the power 3 or 1 by 2 into 2 into 2. Similarly, 2 to the power minus 4 is 1 by 2 into 2 into 2 into 2. This is equal to 1 by 7 2's. You have 7 2's over here, which is equal to 2 to the power minus 7 or 1 by 2 to the power 7. Alright. Now, let's do a few practice questions. Say you want to do minus 3 to the power 4 into 5 by 3 to the power 5. Now, first let me split these numbers and open these brackets. You have a negative number raised to an even power. This will give you a positive number, right? Why? Because minus 1, for example, minus 1 to the power 2 is equal to minus 1 into minus 1. And if you have an even number of negatives, if you multiply them, you will get a positive. Alright, so I can write minus 3 to the power 4 can be written as just 3 to the power 4. And by opening this bracket over here, I can write it as 5 to the power 5 divided by 3 to the power 5. Alright, so this is the expression. Now over here I have the base 3 and over here I have the base 3. So this can be simplified based on the rules that we have discussed as 3 to the power 4 minus 5. And you multiply it with 5 to the power 5. This simplifies to 3 to the power minus 1 into 5 to the power 5, or it can be written as 5 to the power 5 divided by 3. Let's do another question. Alright, over here you can see that I have 2 and I have 2 over here as the base. So 2 to the power 6 divided by 2 to the power 7 can be written as 2 to the power 6 minus 7. Let me write that over here. So that's 2 to the power 6 minus 7 to the power 3 into 2 to the power minus 4. Alright, now 2 to the power 6 minus 7 is 2 to the power minus 1 to the power 3 into 2 to the power minus 4. This can be simplified as 2 to the power minus 1 into 3 based on the rules that we've learned, and I get this expression over here. So this is minus 3 and this is minus 4. You have the same base in these two exponents. So this simplifies to 2 to the power minus 3 plus minus 4, which is equal to 2 to the power minus 7. Alright, let's do the next problem. Say you want to simplify 3 by 4 to the power minus 2. Let me open the bracket and take minus 2 and give it to the numerator and the denominator. So that's 3 to the power minus 2 divided by 4 to the power minus 2. Now we know that 3 to the power minus 2 is equal to 1 by 3 to the power 2. In a similar manner, 1 by 4 to the power minus 2 is equal to 4 to the power 2. Using this expression simplifies to 4 to the power 2 divided by 3 to the power 2, which is equal to 16 by 9. Alright, let me make some space before we do the next problem. Let's try this problem now. Alright, now to start with, let me open these brackets and take the powers in. Alright, so this becomes 1 divided by 3 to the power minus 3 minus 1 divided by 2 to the power minus 4 divided by 1 divided by 4 to the power minus 3. Alright, now 1 divided by 3 to the power minus 3 is equal to 3 to the power 3 and minus, I have minus over here, and this simplifies to 2 to the power 4. Right, now let me divide this with 4 to the power 3. Now 3 to the power 3 is 3 into 3 into 3, which is 9 into 3 is 27. 2 to the power 4 is 16. This is 27 minus 16 divided by 4 to the power 3. So I get the answer as 11 divided by 4 to the power 3, or 11 divided by 64. In this video, let's learn about having a fraction or a rational number in the numerator. So we have 4 to the power 1 by 2 over here. Now this is equivalent to writing the square root of 49. Remember, when you have a radical sign like this over here and you don't write anything over here, it's understood that you take 2 over here. So 49 to the power 1 by 2 is the same as the square root of 49. That's an interesting thing. Now we know that 7 into 7 is equal to 49. Therefore, the square root of 49 is equal to 7. You can note that the square root is the inverse operation of raising a number by the power 2. Like you have square root and you have taking the power 2. These two are inverse operations. Now, if you have 32 to the power 1 by 5, what do you mean with that? So I can write 32 as 2 into 2 into 2 into 2 into 2. That's 5 2's, and you raise it to the power 1 by 5. So raising it to the power 1 by 5 means if you have 5 similar factors, that is from a group of 5 you take 1. So this simplifies to 2. This can also be written as 32 taking the fifth root of 32. So this expression and this expression means one and the same thing. Now let's try to find out 32 to the power 2 by 5. I can write this as 32 to the power 1 by 5 to the power 2, right? Because a to the power mn can be written as a to the power m to the power n based on the rules that we've learned. Now 32 to the power 1 by 5 is equal to 2. So that's 2 to the power 2, which gives you the answer as 4. Let's practice a few more questions. Say you want to simplify 4 to the power 5 by 2. I can do this as 4 to the power 1 by 2 to the power 5. 4 to the power 1 by 2 is nothing but the square root of 4, which is 2. So this simplifies to 2 to the power 5, and 2 to the power 5 is nothing but 32. Alright. Now you could also have done it in the opposite manner, like you could have taken it as 4 to the power 5 to the power 1 by 2. In either way, it simplifies to 4 to the power 5 by 2, right? Now let me expand this. This is 4 into 4 into 4 into 4 into 4. You have 5 4s over here, and then you have your power 1 by 2 over here. Now when you raise a number to the power 1 by 2, from every 2 you take 1, right? So you have 2 4s over here, you take 1, you take 1 4 from these 2 4s, and 4 can be written as 2 into 2. So from this you take 1 2, right? So therefore this is equal to 4 into 4 into 2. 4 into 4 is 16. 16 into 2 is equal to 32. Alright, now you can see that a to the power m by n is nth root of a to the power m. That's what we did over here, right? We've taken the root first and we've taken the power later. Or you can do it like this, where you do the power first. So you have taken m over here and you take the root. That's the root over here. So both of these are this one and the same. And remember, n has to be not equal to 0 because division by 0 is not defined. Alright, let's do a few more practice problems. Say you want to simplify 3 to the power 2 by 3 into 3 to the power 1 by 3. You can see that the base is the same over here. Therefore, this is nothing but 3 to the power 2 by 3 plus 1 by 3, which is equal to 3 to the power 1 or just 3. Alright, now say you want to do 11 to the power 1 by 2 divided by 11 to the power 4 by 5. This is equal to 11 to the power 1 by 2 minus 4 by 5, because you have the same base over here, right? Now 1 by 2 minus 4 by 5, you can simplify it by changing 1 by 2 to 5 by 10, and 4 by 5 can be changed to 8 by 10. So this simplifies to 11 to the power minus 3 by 10. 5 by 10 minus 8 by 10 is equal to minus 3 by 10, right? Alright, now you can simplify this as 1 divided by 11 to the power 3 by 10, because we know a to the power minus n is equal to 1 divided by a to the power n. Using this rule, we can write it like this. Let's do one more question. Say you want to simplify 19 to the power 1 by 7 into 11 to the power 2 by 7. Alright, now you can see that the denominator over here is 7 and the denominator over here is 7, but the numerator is not the same. So to use the rule where the base is different but the exponents are same, let's try to make some manipulation over here. So I can write this as 19 to the power 1 by 7 into 11 square to the power 1 by 7, right? Now I can see this power and this power is the same. So this can be simplified as 19 into 11 square to the power 1 by 7. 11 square is 121. We make some space. You can do the multiplication. 19 into 121 will give you, how much will that give you? It will give you 2299. So this simplifies to 2299 to the power 1 by 7. Hi students, in this video, let's analyze even and odd numbers. So let's start with even numbers. What are even numbers? Let's take some examples. We have -4, -2, 0, 2, 4, etc. All of these are even numbers. So even numbers are of the form 2x, where x is any integer. Alright, so you can see that every even number will be divisible by 2. Alright, and what about odd numbers? Any number that is not even is an odd number. For example, -1, 3, 7, 9, etc. Alright, now we have established what even and odd numbers are. Now let's discuss some important properties with respect to even and odd numbers. Now let's start with three properties. Say you're adding two even numbers, you're adding two odd numbers, you're adding an odd and even number. Can you tell me whether the answer in each of these three cases will be even or odd? Now we start with even plus even. If you add two even numbers, the answer will always be even. Let's take an example. So for example, if I add 2 and 6, my answer is 8. 8 is even, right? If I'm adding minus 2 and 6, my answer is 4. The answer is even. If I'm adding minus 6 and 2, my answer is minus 4. This is also even, right? So you can see that whenever you add two even numbers, the answer will always be even. You can also think of it in this way. I can write the first even number as 2a, right, in respect of 2x, where a is some integer, right, and the second even number could be 2b. So when you are adding them, that's 2a plus 2b, which is equal to 2 into a plus b. Again, this is also an even number because it's of the form 2x. So whenever you are adding two even numbers, your answer will always be even. Alright, let's proceed. What about whenever you add two odd numbers? Let's take some examples to understand this. So for example, two odd numbers would be 3 and 7. So when you add them, you get 10, which is even, right? Say let's take some other example. Say 1 plus 9. So again you get 10. If you take 3 and say 11, so 3 plus 11 is 14. This is also even. So whenever you add two odd numbers, the answer would be even. Alright. So why is that so? Because you can write any odd number as an even number plus 1, right? So over here, let me write the first odd number as even 1 plus 1 and the second one as even 2 plus 1. So whenever you add this, even plus even is even and 1 plus 1 is 2, which is also even. So again, you get an even number. So that's just a way of thinking about it. But the best way to understand it is with the examples we have seen. Alright, so odd plus odd always gives you an even number. Now the third case that we discuss over here is odd plus even. So again, let's take some examples to understand this. Now I could take 1 and 2, right? 1 and 2. So 1 plus 2 is equal to 3. You can see that it's odd. If you take another example, 7 plus 4. 7 plus 4, again, that's equal to 11. This is also odd. So odd plus even always gives you an odd number. Alright. Now, over here we have discussed the case where we are adding. Now, what about subtraction? Let me make some space over here. Now, even minus even, you will see that that is always even. Why is that so? You can think of it in terms of examples, or you can just take this even to the right hand side. So that becomes even minus even, and again, that's even. Let's take some examples. 6 minus 4, that's 2. Or 6 minus 8. That's minus 2. All of these are even. So even minus even gives you an even number. What about even minus odd? So from here you can see that even minus odd will be an odd number, right? So if you take this over here, that's even minus odd, and you take this one over here, that's odd, right? Negative of odd is odd. So even minus odd will always be odd. Let's take an example. 6 minus 1, that's 5. Or let's take 10 minus 3, that's 7. So these two you can see are odd. So even minus odd will always give you an odd number. What about odd minus odd? Odd minus odd will give you an even number. Let's see that over here with an example. I have 7 minus 1, that's 6, right? Or let me take 9 minus 3, that's again 6. So all of these are even. You can also think of it in this way. If you take this minus odd to the right, it becomes odd is equal to even plus odd, which is what we have over here, right? Therefore, odd minus odd will always be even. Alright, so these are some interesting properties which will be used in a lot of questions. Alright, now let's proceed and see the case where you divide an odd number with 2. So what remainder would you get? If you take an odd number, any odd number, and divide it with 2, your remainder would be 1, right? For example, 7 by 2, that gives you a remainder of 1, right? If you take minus 7 by 2, what would that be? Again, it will give you a remainder of 1. Why is that so? Minus 7 is equal to 2 into minus 4 plus 1, right? You can see that this is minus 8. Minus 8 plus 1 gives you minus 7. So you can get it as 1 always over here. Now another interesting property is any even number will end with 0, 2, 4, 6 or 8. This is the basis on which we derive the rule for the divisibility by 2. You can see that in the section where we discuss divisibility rules. Alright, now if even numbers end with 0, 2, 4, 6 or 8, can you tell me what would be the digits with which any odd number can end? That would be 1, 3, 5, 7 or 9, which is just the remaining digits. Alright, so we have seen over here addition, we have seen subtraction, right? Now let's see multiplication. If you multiply an even and odd number, you will get an even number. Why? Because over here you have an even number, therefore the product over here will have 2 as a factor and hence the product will be even. Let's take an example. Say I multiply 4 and 3. So that's even into odd. That's equal to 12, which is even, right? Alright, now if I multiply two even numbers, again that would be even because over here you have a factor of 2. So for example 4 into 6, that's 24, which is even, right? Now if you multiply an odd number with an odd number, then the product would be odd because the product does not have 2 as a factor, right? So let's take an example. 3 into 7, that's 21 and 21 is odd. Alright, so these are some interesting properties with respect to even and odd numbers that we have seen over here. Now one more thing to keep in mind, decimals are neither even or odd. Alright, only integers are even and odd. Okay, and one more thing to be kept in mind is 0 is an even number. Why is that so? Because 2 into 0 of this form where x is 0, you get 2 into 0, that's equal to 0, right? Therefore 0 is an even number. And remember, just a side note, 0 is neither positive nor negative.